Let's look at the solution to this problem. One thing that's going to be important to note is that because it says that their system is frictionless and has air resistance is going to be negligible, until we get to part E where we do start accounting for friction, none of our energy should be converted into heat, and also there are no external forces on our system that are going to do any work on it, so we should be able to use conservation of mechanical energy. The first thing I want to do is add to my diagram all of the information that's not already on there. So they tell us that the speed at point C is 4 meters per second. So we'll draw our block in at point C and label the speed of C as 4 meters per second. They also tell us up at point A, our speed at point A is going to be 0 because it's at rest. And they also tell us the mass of the object.
Please excuse the interruption. Andrea Burnich, would you please call me at 50110? Again, Andrea, 50110. Thank you.
Is 0.1 kilograms. And in part A, we are looking for the height at part A. Height in our energy stuff is going to be connected to gravitational potential energy. And instead of actually calling it h in the equation, we look at the y position. And so we'll call this the y position at point A. That's what we're actually trying to find. So if we set this up using conservation of mechanical energy, so this is part A. We know that the energy that we have at point A should be equal to the energy that we have at all of our other points. At point B, it is both up in the air, and we can tell it's going to be half a meter up because it's one radius up, but we don't know its speed at point B, so that's not going to work. We do know for part C, though, that it's half a meter up in the air and it's moving 4 meters per second, so we can figure out the total amount of energy at point C. So we'll relate the energy at point A to the energy at point C. At point A, it's only going to have gravitational potential energy because it's up in the air, but it does not have any speed, so it should not have any kinetic energy. So my energy at point A is going to be gravitational potential energy. And at point C, it is both moving and off the ground, and so it is going to have both a combination of kinetic energy at point C and gravitational potential energy at point C. We know gravitational potential energy is m times g times y. So that's going to be mg times the y position, or the height at point A, equals 1/2. M for kinetic energy is 1/2 mv squared, so 1/2 m times the speed at point C squared. And then gravitational potential energy at C is mg times the y position for C. We said we were trying to solve for the y position at part A, which is right here. I can see my masses are going to cancel out. And so all I should need to do is divide gravity off of each side, and I'll have my answer. So this is going to be 1/2. The speed at point C is 4 squared plus g. We'll use 9.8. The y position for C is half a meter divided by g. 9.8, and that should come out to be 1.32 meters. We don't have a whole lot to tell if that's reasonable, but it should definitely be more than half a meter, which it is, and so that seems good. We'll go on to part B. In part B, we're just being asked to complete a free body diagram for the object at point B. And so this shouldn't be too bad. Since there's no friction and there's no air resistance, there's not a whole lot of forces left that we can have. We know there's always going to be a force of gravity. And we can see it's on the track, and so there should be a normal force from the track acting on it. And since the normal force is always perpendicular to the surface itself, the normal force is going to have to point to the left. And that is pretty much it. You'll notice it is going in a circle, but it is not in uniform circular motion like we had talked about in our previous unit, which is why we don't have...
Mr. Passmore, please 50400. Mr. Passmore, 50400, please.
Which is why we don't have the net force pointed to the center. We'll talk more about non-uniform circular motion in the future, but just so you can sort of see why this works. As the object comes down and starts to go through the loop, as it's going through B, it's going to be going up in a circle, but it's going to be slowing down as it loses potential energy, or loses kinetic energy and gains gravitational potential energy. And so the free body diagram, the forces, should show why this is going in a circle and slowing down. And so we still, to go in a circle, even for non-uniform circular motion, are still going to have a force towards the center. And just like we saw in one-dimensional motion, if we want something to slow down, there needs to be a force going in the opposite direction it's moving. And the force of gravity in this case is going in the opposite direction B is moving at that point. And so this force will explain why it goes in a circle, and this force will explain why it's slowing down. In part C, never mind, part C is not included. Part D, we were asked to determine the maximum height above the ground attained by the block after it leaves the track. So after it leaves the track, it's going to become a projectile. And you certainly actually can solve this problem as a projectile problem, and on the AP test, you would get full credit for doing so. However, since we are in the energy unit, we should make sure that we know how to deal with it using energy. And so I'm going to talk about the block when it's at our maximum height. We'll call that point D. And we know at point D, it's obviously going to be up in the air. That's actually what we're trying to find. Continue our ground. So we're trying to find this. That's going to be the y position at point D. So that's what we're trying to solve for here in question D. The thing to remember is that when we're looking at our energy, we're going to have gravitational potential energy because we're up in the air, but the object is not at rest. It is still moving, not up or down, but it is moving to the side. And so we're still going to have some kinetic energy. And this is going to be based on the the speed in the x direction. And so we can talk about Vx. And we know from our projectile problem that that is going to be the same as the x component of the speed at point C over here, because this is like our muzzle velocity. And so we got to figure out what Vx is right there. So as far as our conservation of energy part of the problem goes, we know the energy at point D should be the same as, we'll connect it to C, because that's what our initial information was about. And so the energy at point C should equal the energy at point D. Both of these are off the ground, so they're both going to have gravitational potential energy. I guess we could call this height 0 if we wanted to, but since the question is ultimately asking us to figure out how far this is off the ground, it's probably easier to just treat the ground as 0. So they're both going to have gravitational potential energy. They're both moving, so they'll both have kinetic energy. That means our total mechanical energy at C and D is a combination of both kinetic and gravitational. So our kinetic energy at point C plus our gravitational potential energy at point C equals our kinetic energy at point D plus our gravitational potential energy at point D. So we'll replace those with 1/2 mv squared and mgy for our two types of energy. So 1/2 m times the speed at point C squared plus m times g times the height at C equals 1/2 m times the speed at point D squared plus m times g times the height at point D. Mass cancels out. Remember, we're trying to find the yd here. And so we can solve for this by subtracting our 1/2 vd squared to the other side and then dividing by g. So we'll get yd equals 1/2 vc squared.
Please excuse the interruption. I'm looking for a student. The name is Lanaya Trotter. Your transportation has arrived. If you would report to the front door, please. Lanaya Trotter, please report to the front door. Thank you.
All right, we know VC is 4. We know G. We know YC is 1/2 meter. And so we just need to figure out the speed at point D, which we said is the x velocity. So we'll set up our projectile initial configuration. We know this is 30 degrees. We know that our muzzle velocity is 4 meters per second. We're looking for Vx, which is going to be the hypotenuse times the cosine of our angle, so 4 cosine 30. And so we should be able to just plug everything into this equation and get our answer. And so we're going to have 1/2 times 4 squared plus 9.8 times 0.5 minus 1/2 times 4 cosine 30 squared divided by 9.8. And if we calculate that out, that should give us 0.704 meters. And if we check that out, that seems reasonable. This is 1/2 meter, so we know it has to be more than that, which 0.704 is. In part A, though, we figured out this height here at the beginning was 1.32 meters. And since we've still got some kinetic energy here, it's not going to have as much gravitational potential energy as it did at point A. And so we know the answer for the height at point D has to be in between the heights at A and C, which it is. In the last part, part E, they ask us to figure out if there actually was friction involved. And in order to get to this final speed, we needed to not drop this from 1.32 meters, but instead drop it from 2 meters. How much work did friction do? And so we'll replace this with 2 meters. And so I think the easiest way to think about this is we know work is just the change in energy. And so we still have the same ending conditions. So our final conditions haven't changed. It's our initial condition that's going to change. So change in energy is the final condition, or the final energy minus the initial energy. And at the final point, that's point C. So the final energy is going to be a combination of kinetic plus gravitational potential energy. And the initial point is going to be over here at point A. And we know it has no kinetic energy because it's not moving, so it only has gravitational potential energy. So it'll be the gravitational potential energy at point A. And so really what I'm doing here is I'm subtracting the mechanical energies, and I'm going to figure out how much the mechanical energy changed. Obviously, the total energy of the system is going to stay the same because when it gets converted, when friction generates some heat, it's just going to warm up the block and the track and stuff. But we're still describing a certain change in energy. And so the work done by the frictional force is going to be the same as the amount of mechanical energy we lost because the friction is going to convert that energy into heat. And so I can just calculate these. The kinetic energy at point C, once again, that's 1/2 mvc squared, plus the gravitational potential energy, mgyc, minus mgya. We can't cancel mass out this time because we're actually looking for a number, so we'll just need to plug all of our values in. 1/2 times 0.1 kilograms times our speed of 4 squared plus 0.1, 9.8, 0.5. Remember, we've changed the height at point A to be 2 meters. We got to make sure we use that. And this should come out to be negative 0.67 joules. And so if we think about only mechanical energy and the types of energy we can calculate, it looks like the system had less energy than it did at the beginning, because when we subtracted our ending amount from our initial amount, we got a negative number. So it looked like we ended with less than we started with. And that's because at the end there's some thermal energy that's not being accounted for here. And so this makes sense. The negative sign tells us that we lost energy. So we lost mechanical energy because it got converted to heat. Or we could call it thermal energy if we want to. And this, although it's not technically right to refer to the energy as being lost because it's still in the universe. We can't have energy be created or destroyed. This is the way that we often talk about it. Our shorthand is we say the energy is lost because it was lost from the useful part of the system. It's not stored as mechanical or potential, or it's not stored as kinetic or potential energy, either one of our types of mechanical energy are in our system. And so it has been lost as far as the useful part of the system goes.